Okay, it's 1 o'clock. All right, let's get started. I want to mix it up today. I actually want to start with group coding. And I also want to mix it up in that I'm not going to make one main portal for everybody to join. I would like people to get into groups of around 4, just with people sitting nearest to you. And then one of you start a portal and send it to each other. And then I want you to take, just kind of merge your homeworks. Make a print function that, does something weird after you print something 3 times, but then add something else cool to it. And then we'll come together in, let's say, 5 minutes and, just talk about what happened. So, I don't know. Go. Okay, so whether or not you finish doesn't really matter. I've sent out a portal link. Could one person from each group join the main portal and copy and paste what you came up with onto the main portal?
Can I host a portal and join a portal? Just out of curiosity.
Yeah, I think so.
So just throw in some.
It doesn't matter if you finished. I just want to, I don't know.
I don't remember anything particularly.
How do you run things on Atom?
On Atom? If you want to run it in Atom, you have to get a plugin.
We can't run our code.
Not without a plugin. They do make plugins for it. But what I do is I just have a terminal up here,
And then you run it in there.
Yeah, so I'm in the same directory as Atom now. Now if I want to run this file, I just, it's Python 3 prints.
Where you can get terminal in Atom as well. Yeah, I have terminal.
I know there's a plugin, I just don't have it. But
Let's just throw in a number and whatever you want.
How do we join his thing?
You just send out the link.
And whoever in your group joins the master portal, could you comment all the computing IDs for attendance? All right. So, oh, man. There he is. I can tell what that is on my screen. Can you guys tell what that is? I can tell on my screen because I can look back far enough.
Is it? You can zoom out.
Oh, that's true. That's true. Yeah.
What's the library? Oh, it's just.
Now can you tell who it is?
Too far. Oh.
That's our emperor. That's great. All right. Does anybody want to share the esoteric behavior they added?
It just gets more angry if you do it 10 and then 100 times.
It gets pretty. Yeah. Nice. I saw you did the Darth Sidious, right?
Yeah. So
yeah.
if you print the same thing 3 times in a row, it prints the tragedy of Darth Plagueis the Wise, which is that long one there. And then anything you print after that, it prints that nice picture of the Emperor for you. And then there's just a bunch of other random triggers. Like if you print hello there, it prints General Kenobi, you're a bold one. If you try to print the float form of 3.14, it'll print tau is better than pi.
Oh man.
And just other.
So this is kind of like a very meme-oriented print function.
Like.
Yeah. Oh, true. Anybody else?
So every third line or whatever, I used a TK interframe to display a meme.
Oh, nice. Very good. Excellent. Well, cool. All right. I would go through what you guys just put up here, but I want to move on with the slides. But I just wanted to test how it would work using kind of divide and conquer group coding. How did that work out? Is that okay? It's good? Nice? All right, cool. Well, so maybe we'll do that more in the future. By the way, I want to get to the slides here because this is a really important slide set. Closures. Who has heard of closures? Okay, a couple people. Well, they're amazing. They're extremely powerful. and it turns out that you all use them. They just go by another name, which you're more familiar with. But before we get to closures, we have to talk about arguments a little bit. Who knows about keyword arguments? I'm aware that they don't teach it in 11.10, so I'm assuming that you guys don't know about keyword arguments. And I'm sure they don't teach you packing and unpacking, so we'll go over some argument stuff, and then that'll lead us into scope, and finally closures. So everybody's familiar with the classic positional arguments, right? So this is a function that takes in a coefficient, a base, and an exponent, and takes the base to the exponent, multiplies it by the coefficient. Pretty straightforward. And if we call it on 10, 2, 3, what do we get? It's not a trick question.
80.
80, yep. 80. All right, now what do we get? Oh, sorry, no, this isn't a call. So here we're redefining the math function. We've still got the coefficient, the base, and the exponent, but here we've put equals 1. This means that 1 is going to be the default for exponent. And this is kind of Python's way of doing method overloading. So like in Java, if you want to have a default for a parameter, what you do is you'd overload that method so that if you call the method without that parameter, it'll use the default value instead. Python doesn't really have that. Instead, it has these default arguments. So if we specify exponent to be 1, now if we call math on 10, 2, what do we get? 20, yeah, because the exponent by default is 1. So there's another way you can use keyword arguments. So here we specified a default in the definition of the function. You can also use that notation, that exact same syntax, when calling a function. So here, instead of just passing in numbers directly, we're passing them in, but we're pairing them with exactly which parameter we want to pass them in for. And this allows us to override the order of parameters. So here, when we call math, this is the coefficient and this is the base. But if for some reason we want to pass in parameters in some different order, what we could do is we could refer to the parameter we're passing by name. So here, exponent is going to be 2, base is going to be 2, coefficient is going to be 1, despite this not being the original order that the parameters were defined. Does that make sense? And so what do we get here? 4, yeah. Because coefficient is 1, base is 2, exponent is 2, 4. So we can override the position of arguments by passing them in by keyword. Yeah. So there's an analogy here that'll come up later. You can think of arguments passed in this way as passed in like a tuple. We're passing them in order. And what's in order? Tuples. Tuples are in order. So here we have a tuple of arguments. But what is this like? This is like a dictionary, right? We're passing in arguments, but we're associating them with a name that we want to pass them in by. So here, this is like passing them in by dictionary. So this will come up later, because it turns out that that's exactly what's going on under the hood, and we can take advantage of that. All right, here's one more. We're redefining math again. This time, we've got exponent is 1 by default, and coefficient is 1 by default. And base has no default. This doesn't work. Python requires that all keyword arguments go at the end. Or, sorry, all default arguments go at the end. And this is to avoid ambiguity. If you mess around with it some on your own, you'll see how if this were allowed, it would cause some really weird behavior. So just something to keep in mind. I'm not, it's not a big deal, but basically just be aware of this. The keyword arguments have to go at the end. Okay, who knows what packing is? Okay, awesome, great. No one, or one person. Sorry, should be more exact. So we've all probably encountered this problem. What if we want to make a function that takes in multiple arguments? How would you solve this problem? Anybody? Var args. Okay. How would you solve it in Java?
Use the ellipses.
Okay. Yeah. Well, how would you use it without those? You would pass.
Can you pass it on with?
Yeah. Yeah. If you didn't want to use those features, what you could do is just pass in a list of all the arguments. Well, it turns out in many languages there's a way to avoid having to pass in a list, and this is that way in Python. It's called packing. And basically, here, if we define a function with a parameter, if we put a star before that parameter, what this is going to do is collect all of the positional arguments that were passed in, no matter how many there were. So let's write this mult function. It takes in args, and it represents this as a tuple. So just like I was saying, that analogy is actually fact. When we pass in positional arguments, it's passed in as a tuple, and this is that tuple. It's the tuple of arguments that we passed in. So we're going to loop through that tuple and multiply everything, and then return the result. So what do we expect here? Oh, that's a lot of math. Basically, it multiplies the arguments just like how you'd expect. And you'll notice we didn't have to put a list around these arguments. We just passed them in, and this one variable collected all of them. And this is the packing. All of these arguments are packed into one variable.
Is args a keyword, or could that have been named anything?
Can be anything. Yeah. It's usually called args, but if you're writing a function where it makes sense for it to be something else, then sure. Like you might want to call it star operands or something, star, yeah. Now, what about this? What happens here?
It would just output 1 because of multi-arrays included.
Yep, basically we're passing in an empty tuple here, so there's nothing to iterate over, so we're going to return 1. Now, this is kind of weird. We didn't really expect this because we didn't pass anything in. Like, what's nothing multiplied by nothing? No, nothing, right? This shouldn't have worked. So how would we guarantee that at least one thing is passed into args? Any ideas? Star args equals 1. I mean, that's a good thought.
Put in another parameter before it.
Yep. What we can do is we can combine star args with other positional parameters. So, like, let's take this mult function. It takes in num and then star args. And so basically what this is going to say is take the first positional parameter, call it num, and then all the other positional parameters pack it into args. So now this won't work because we failed to pass in the one required argument num.
If you did like star args equals 1 or something like that, would it like make a tuple of tuples? Would it?
I don't know if what that would do. I've never tried it. Star args equals. I think if you were to do that, you would have to say equals some tuple, because what you'd be doing is specifying the default. And so since star args is a tuple, you'd probably have to say star args equals the tuple containing 1 or something like that. But I'm not sure. Try it. Does this make sense to everybody? This is packing. Okay? So you might be wondering, remember, just...
It doesn't even let me...
It doesn't let you? Yeah, that makes sense. I don't know. I don't know what should happen there. So remember, just like 2 minutes ago, we were passing in arguments by keyword. And we said that was kind of like a dictionary. So how do we deal with that, right? Because this is a tuple. This tuple is not a dictionary. Oh, wrong segue. First, I'm going to talk about keyword-only arguments. So before we had num before star args, right? Now we've got num after star args. Does anybody know what's going to happen here? It's going to complain because any arguments that are declared after the star argument are keyword-only arguments. This means that you can only pass them in by keyword. And this is because Python basically can't tell where this tuple ends and the positional arguments begin. So it's going to force you to pass this in by keyword. What that means is the only way to call this function, I guess I'm not going to show it, is to say 2, 3, 5, num equals 10. So, and it turns out we can use this for some really, really clean coding practices. What you can do is you can actually put a star in your arguments list with no variable name. And what this is going to do is collect all the positional arguments and then throw them away. And so basically, this is a function for which you cannot pass anything in positionally. You can only pass things in by keyword. So it's going to complain, we gave it 2 positional arguments. We gave it a tuple of 2, and we're saying we don't take in tuples of arguments here. We just take in these 2 keyword. So now you might be wondering, like, why on earth would you do this? Well, the reason is often we write functions where there's no order for the parameters that really makes sense, right? So you might write a function that, takes in a folder and a name and, a time. There's no reason why the parameter should go in the order folder, name, time. They could have gone name, folder, time, or time, folder, name. So in situations like that, where it's not clear what the order should be, it's actually considered really good practice to say that you cannot depend on there being any order. You have to specify the keywords. This prevents bugs because that way no one's going to accidentally pass in time for name. They'll have to look up the keywords, and they'll have to associate each parameter with the keyword. Does that make sense? So this is one application. So as you can see, it guarantees that we're very explicit. Okay, back to what I was saying about the dictionary. We want to be able to pack arguments that are passed in by keyword. How do we do that? With star quargs. And this is so much fun to say. Let's all say it together.
Star quargs.
Star quargs. Yep. It'll sound like a real nerd in Thornton Stacks. It'll be like, def main star quargs. Really, it's a good way to really boost your nerd points. Yeah. So what this does is it's exactly the same as star args, except that it collects all of the parameters that were passed in by keyword into a dictionary. So here's just basically a function that packs everything, right? Because we can only pass things in by position or by keyword. There's no other option. And so basically this function is going to collect everything that gets passed in and put it in one of these 2 data structures. And so we're printing out both. And if we call the function with some positional and some keyword arguments, we get exactly what we expect. The tuple containing 1 and a, and the dictionary mapping the string hello to the string world and the string test to 1, 2, 3. Now, one interesting side effect of this, and you might already have noticed something weird, is that the act of using star quargs converts these plain text names to these ASCII strings. So this is actually kind of a subtle artifact of metaprogramming. We've converted a keyword to a string without even really intending to. So just kind of interesting. Any questions about this? It might not seem super relevant yet, but it turns out that what we're about to talk about, it's very useful to write functions that take in any arguments whatsoever. So it's gonna be useful to be able to take in whatever.
So do you just have to have a bunch of if statements, like if this key is in the quargs dictionary, do something for every single possible case, or is there? Because how would you know if the user could they just make up a keyword?
Yeah, they could make up a keyword. Yeah. So yeah, args is used all the time. Args is really useful. Quargs is a little bit more. It's harder to come up with examples for quargs, but it is useful. If you've got functions, for example, that take in Yeah, like arbitrary keywords. If you wanted to say like, it's tricky to come up with an example for quarks, but it's necessary. It has to exist because, like I said, later on we're going to want to write functions that take in literally anything. So that's our way of collecting anything. Okay. That's right. Yeah. So just like how when we're declaring a function, we have to put all the positional arguments before all the keyword arguments. Same goes with when we're calling a function. We have to put all the positionals before all the keywords.
Even like the function packing up there, if you wrote an argument with a keyword and then passed in something assigning it to that keyword, so if you wrote like hello, comma, star args, comma, star star quarks, would it save it in quarks as well? Or would it be its own variable?
I believe it would save it in its own variable.
Okay.
But I'm not 100%. You try it.
Okay.
Like I said, quarks is not super common, so it's more of a necessity than it is an actual feature. Okay. So we've gone over packing. There's an inverse of the packing mechanism. It's called unpacking. And what it means is that just like how we could write a function that collects an arbitrary number of parameters into one variable, we can call a function which divides like a list into the variables. You'll see. So this is the print method signature, okay? When you call print, this is what you're calling. It takes in star objects, which means that you can print any number of things, okay? And then everything after this, because there's a star parameter here, everything after this is keyword only. So we can print any number of objects, and then we can specify by keyword what we want to separate those objects by, the end of the line, and what file we're writing it to, and I forget what this does. But just so you know, that's the method signature for print. So let's take this array here. It's got test 1, 2, 3. One way we could print everything in this list is by saying print array 0, array 1, array 2, array 3. This is kind of tedious. And what if we don't know the length of the array? Then there's no way we could write it out if we don't know the length. So that's what unpacking is for. We could alternatively write it like this, print star array. So when you're defining a function, if you put a star before the parameter name, it collects variables. When you're calling a function, if you put a star before your variable name, it splits that data structure up into separate parameters. Does that make sense? And that's called unpacking. And it works for quarks too. So we've got quarks, sep equals comma space, end equals bang new line. So now if we run print star array star star quarks, we get test comma 1 comma 2 comma 3 comma 4 exclamation point, because we unpacked this dictionary of keyword arguments into the print function.
Why is star necessary for the print function?
It's not so much necessary, it's just how they chose to implement it. In Python, the print function, you can just pass in multiple things that you want to print, and it will just print them all on the same line.
Can you unpack any iterable? Or?
Good question. So I'm not totally sure, but basically, if you're unpacking anything that isn't a tuple, it's going to eventually become one. So you can avoid ambiguity by just going ahead and casting it to a tuple and then unpacking it. So yeah, I'm not totally sure, but that's just because I always cast it as a tuple before I unpack, just to make sure I'm not, abusing any features or anything. Does this make sense to everybody? All right, cool. So now we're going to talk about scope very briefly. Everybody knows what scope is, I hope, more or less. So, okay, Python uses names, and you've actually seen that. If you tell Python to print out hello, but you haven't defined hello, it'll give you a name error. That's because the string hello to Python is represented as a name object, and that name object is not defined. So we get a name error. Now, scope of a name is the block for which that name is defined. Scope in general is just a block where any new names will remain defined. Does anybody have an idea for what enclosing scope means? Any thoughts? No? Okay, that's fine. Enclosing scope is just a scope that contains a scope. So let's say we have a variable x. We could ask, what's the scope of that variable? Well, it's everywhere where that name is defined. What's the enclosing scope of that variable? Well, it's the scope around the scope where that name was defined. Does that make sense? That's the enclosing scope. And the universal enclosing scope is the global scope. So here, what's the scope of this param? Yeah, well, or no, this param, the scope is just bar here. It only exists in bar. What's the scope of this param? Yeah, all of this. So, and you'll notice one interesting thing I'm doing here, which you might not have known you could do. You can actually define a function inside of a function. All right? Just let that sink in because it's very important. This is a function definition, but Python is a scripting language, which means that the definition of a function is script, which means that we can actually call that script anywhere. We can call it in the global scope, but we can call it within another scope as well. So here we're defining foo, and this creates a scope. As soon as we define foo, we've got the foo scope here. And then right here, we're defining bar, which makes a new scope. And the enclosing scope of the bar function is the foo function. Okay? Uh-huh.
Can the bar function call the foo function?
Can the bar function call the foo function?
A function within a function calls enclosing function?
Yes. Yep.
Can you make a function in an if statement?
Can you make a function in an if statement?
Yeah.
That's exactly what I'm doing.
Oh, I didn't see the if. My bad.
Yep. You can, like I said, Python is a scripting language. Function definitions are script. They're just like any other code. You know, if statements and def statements are just statements, and you can put them anywhere. So here we've got a global definition, and here we've got an inner function definition. So does anybody feel uneasy? Yeah? Yeah, James feels uneasy. All right, now I want to talk about a concept called free variables. Who's taken linear algebra? Good number of people, great. Well, free variables mean basically the same thing in both scenarios. So let's say we've got a main function here, and we define this local variable offset, okay? What's the scope of offset? Main, everything in main. All right, now we define an inner function, math. Takes in A. What's the scope of A? Math. All right, we define a local variable B, scope of B, math. All right, and we return A plus B plus offset. Now we've defined this function. What's the scope of math? Main. Math is just a variable, right? Functions are objects. And we've created a variable called math, which refers to this function object, okay? So the scope of math is main, which means that we can call math right here. It's the name math is still defined right here. So we're going to print math of 5. We pass in 5, b is 1. But look, we got to use this offset variable here. So offset was not defined in this function. It was defined in the enclosing scope. I just want to point that out. Now if we reset offset to 100 and now print math5, what's going to happen? Any ideas? What do you guys think this is going to print? Just shout it out. 16? Okay, what is this going to print? 106? 16 still? I guess maybe the fact that I called this slide free variables is a giveaway, because the variable is free. You know, referencing offset here does not lock in the value of offset. The variable is free. It's allowed to change. So we've changed the variable and we call the exact same function again, and we got a different result. Does this sound familiar? All right, if it doesn't, we'll get to it. Oh, important thing here. Note, I also printed out math.dundercode.co freevars. This is actually reflection. And it printed out offset. So we can actually see directly exactly what the free variables of the math function are. It's offset. Offset is the free variable of math.
So what if you return your math function from all of it outside?
Oh, man, you guys are just great at busting my segues. Yeah, that's exactly what a closure is.
Can you run like get attribute on the function and grab that offset variable there?
Get attribute?
Or you can get attribute.
Get so offset is not an attribute of math.
But how would you access that without just the string?
This way.
Isn't that still the string name? Oh, these are string name. Oh, so returns actually variable.
Yeah. Okay, so now, you know what? I am running out of time. I'm going to skip this. Basically, what I'm getting at here is there's a difference between free variables and global variables. Offset is considered a free variable here because it was local in main. But if we hadn't written a main function, if this were all just script in the global scope, then offset would be considered a global variable, and global variables have slightly different characteristics than free variables. So just keep that in mind. Because I want to get to closures. We got 10 minutes, and this is the first real metaprogramming. All right, so here's a closure. We're defining an inner function, but then we're returning it. Without calling it, we're returning the function. Remember, functions are objects, and function definition, this statement is basically like saying close equals function. So we've created a closed variable which refers to this function, and now we're returning that variable just like we would any other variable. Now we call the original function make closure, and we call the result C. And then we're going to call C, because remember, make closure returned a function, so we can call it. Now, what do you guys think is going to happen? Who thinks 2? Who thinks 1? All right. I guess the arrow is kind of a giveaway. It's 2. It's 2. So when you define a function, the function will actually remember its enclosing scope. And even when this scope vanishes, if this function has to remember it in order to work, then it will. So you might be thinking like, x equals 2. I mean, the scope of x is make closure, which means that as soon as this function is over, shouldn't that x go away? The scope is done. We've exited this function. We returned. Make closure is terminated. Why does this x still exist? Well, because it's been closed. A closure is an inner scope which refers to its enclosing scope. And it forces Python to remember something about that enclosing scope, even though it disappeared. So you can see here, x equals 2 was remembered by Python, even though this function is done. X is still 1, by the way. Now let's look at the free variables. The free variables of C are x, just like last time. The cell variables are none. I haven't told you what cell variables are. Now let's look at the free variables of make closure. What do we expect? None. Make closure doesn't close anything, right? Now, what are the cell vars for make closure? Any guess? X, yeah. So you can, just like how you can access the free variables of your closing function, you can access the closed variables of your closed function. You see what I'm saying? They're kind of inverses. So if we want to get the, this variable is very special. If we want to get at it from this side, we reference free variables. If we want to get at it from this side, we reference cell varies.
So what if make closure were to return a tuple of two functions, both of which mutate x? Would they be able to see each other's mutations?
Yep. And if we just access the dunder closure attribute, we get this cell. And this is just complicated Python speak for basically a special variable that's being kept in memory so that we can remember what we need to remember about this enclosing scope. Does that make sense to everybody? Okay. Do you see why I wanted to spend so long on functions being objects? Because to really wrap your head around what's going on here, there's a lot of first-class functions that are being manipulated. So, all right. Hopefully this blows your mind. Classes can also close. So, perfect. So, let's say we have a class ball, right? And it takes in its position, and it has a fly function. It takes a velocity and a limit, and it changes its position based on its velocity while regulating the velocity by the limit. Does this make sense? Basically, this is a speed-limited ball. Now, here's another ball. Takes in a position and a limit, and now when we call fly, it regulates by the limit. So these are two speed-limited balls, but what's the difference? This one, we pass the limit in when we call fly. This one, we pass the limit in when we create the instance. Right? This is the constructor. So every instance of this ball will have its own limit. There's actually one more level we could go. Here, every call to fly has its own limit. Here, every ball object has its own limit. What if we want every class of ball to have its own limit? What we can do is we can write a function called limited ball. It takes in a limit, and it creates a class. And then it's basically exactly the same as what we had over here. But you'll note that now the limit variable is closing this parameter that we passed in way at the beginning. We increment the position. We return the ball, the class. And now what we can do is we can create fast ball. What is this? What is its type? Class. Yes, this is not a ball. This is a class. This is a type of balls. Fast ball. And here's slow ball. And you can see each of these classes has a different limit. Now if we make a fast ball and we call fly, it'll fly 10. If we make a slow ball and we call fly, it'll fly 1. So do you see how we've gone 3 different levels of abstraction here? We've got the upon calling fly level, the upon constructing the ball level, and then the upon making the class in the first place level. Does everybody see why this might be useful? Because what if we want to really make sure that all, maybe this is a game where there's two different types of Quidditch. Let's say this is Quidditch. And we want to make sure that all snitches fly faster than all bludgers. Who's read Harry Potter? Okay, just making sure I'm not like speaking gibberish. So what we could do it this way, but basically it's dangerous because then a user could accidentally make a snitch with the wrong limit. So instead, the right way to do that is to write this closure, which creates a function that can create classes with their own limits. And that way, what we would have is a snitch class, which has a built-in limit. Okay? So this is one application. Here's another application, data hiding. All right. We've got an inc generator, takes in a start, and then an inc function, and the inc function closes on start. Okay? We return start, and we return inc. Now we create an inc variable with our inc generator. Okay? What is this? What is its type? It's a function. Inc is a function. Now if we call inc, we get 1. If we call inc, we get 2. Does this sound familiar to anyone? Yeah? Isn't this exactly what we did last class? Didn't we make a class called inc class? And then we used that class. It had a call function and a count variable. And then we created an instance of that inc class. And then we called that instance. And the individual calls to that instance remembered. Well, it turns out that objects and closures are not so different after all. Basically, this is exactly the code that we ran last time. And it turns out it's exactly the same code because it's exactly the same mechanism. Objects and closures are basically the exact same. Here's a reminder. This was our inc class. Do you see how it's exactly the same? So it turns out that classes are actually just a little bit of syntactic sugar around closures. Closures are the real underlying beautiful data structure. Whose mind was blown today? Oh, sweet. All right, great. That's all I got. So, yeah, have a good week.